Round 2 of related rates introduces some new ideas, including the conical tank, a tank that's an upside-down cone. So let's kind of get this back. There you go. Anyway, we're going to be dealing a lot with cones. So let's start. Water runs into a conical tank at a rate of 9 feet per minute. That's a change in volume again. Conical tank you can model with an isosceles triangle being upside down. I just realized it's 3 dimensions. This is going to lead to some concepts like similar triangles. But if I say dv dt equals 9, the tank stands vertex down and has a height of 10 feet. So I can say right now that that's h. And I can go h equals 10. And then a base radius of 5 feet, so r equals 5. And wants to know how fast is the water level rising when the water is 6 feet deep. Okay, when the water is 6 feet deep, then that's actually h is equal to 6. So I'm going to cross that out and say h is equal to 6, and cross that out because I need to know what the r is when h is 6. So I'm going to do that with a proportion, kind of do the similar triangle thing, and say that h over 5 equals 6 over what? And if we play that right, that's 2 over 1 equals 6 over question mark. And that would be question mark is equal to 3. So when h is equal to 6, r is equal to 3. And that's kind of one of those things we need to know. Okay, so how are we going to set up our equation here, though? Because it wants to know how fast the water level is rising. Well, this is kind of goes back to one of the things we did in pre-calculus where we had to set an equation relative to another one. I know that volume of a cylinder is 1/3 pi r squared h. But now I need to express this cylinder in terms of something else. So what I have to do is say that the ratio of the height to the radius is equal to 10 to 5 or 2 to 1. And it wants to know how fast the water level is rising. That is a dh dt, which means that I need to solve this for a, or I need to actually eliminate r. So if I take this, h over r is equal to 2 over 1, and I solve that for r, I'm going to get r is equal to h over 2. And let's see if that's right. Yep, that's right. I'm going to take that and I'm going to substitute it in, so I get volume is equal to 1/3 pi h over 2 squared times h. And if I simplify that, I get volume is 1, well, let's keep the 1/3 out. Let's just kind of combine the h's. That would be h cubed pi over, this would be 2 squared times 3 over 12. And that gives us my, like the complete, sorry, just kind of checking my work here. But that gives us our complete volume for this. So now we can derive this. dv dt equals, let's do 3 times h. I still have the pi. So this is going to be 3 pi h squared over 12 dh dt. And that can cancel to become 1 and 4. And then we want to solve for dh dt, and I know dv dt is 9, so I have 9 is equal to pi h squared. H was 6, so 6 squared is pi times 36 over 4 dh dt. 36, that's 9. The 9s are going to cancel to become 1 and 1, so I'm going to have dh dt is equal to 1 over pi. If I put the units down, it's feet per minute. Done. So I guess this whole thing with that was unnecessary, but it's going to be necessary later on, so it's good to see it. Okay, next, sand falls from a conveyor belt. When sand falls, it tends to form a right side up cone, falling at a rate of 10 meters cubed per minute. That's a dv dt. The height of the pile is always 3/8 of the base diameter. If I say h is always 3/8 d, which is the same thing as 3/8 times 2r, or 3/4 r. Now I have a relationship between h and r. The first thing it wants to know is how fast is the height changing when the pile is 4 meters high. So I can also say h is equal to 4, but I digress. Let's kind of jump into the equation here. So part A, how fast is the height changing? What is dh dt? Well, we know that volume is 1/3 pi r squared h. And if I want to find dh dt, then I need to solve this original h equation for r. So that means r is 4/3 h. I'm going to plug that in for r, so I get v is equal to 1/3 pi 4/3 h quantity squared times h. That's going to be v is equal to, we have 16 pi h cubed over, and then 3 squared 9, then 81. Let's see, oh no, 27. So now take the derivative. dv dt equals, we're going to have 16 pi h squared over 9, because the 3 and the 9 are going to cancel. Then we substitute. So dv dt was 10, 16, oh sorry, I forgot my dh dt. 16 pi h squared, again h was 4, so that's 16 as well, over 9, dh dt. Do a little bit of algebraic manipulation, which I'll let you play around with. And you get dh dt is equal to, well, I'll show it to you anyway. Cancel that out, you get 5. Cancel one of these out, you get 8. 8 times 16 is 128, and 9 times 5 is 45, so you get 45 over 128 with pi in the denominator, and units on that are going to be meters per minute. Let's come back up, and we're going to do the same process for dr dt. So I'm going to take my volume equation, 1/3 pi r squared, but instead of h, I'm going to substitute this in, 3/4 r. Volume is equal to, this is going to be, let's see, the 3's are going to cancel, so I'm going to have pi r cubed over 4. dv dt, 3 pi r squared over 4 dr dt. So then I have to kind of figure out what r is. So I know h is 4, and r is 4/3 h, so r equals 4/3 times 4, which is 16/3. So plug that in along with everything else. dv dt is 10. 3 pi 16/3 squared is 256/9 over 4 dr dt. 3 and 9 can cancel to 1 and 3. 4 and 256 cancels into 64. And then 64 and 10 cancel into 5 and 32. Okay, if you keep that all straight, what you're going to end up with is dr dt equals, well, you know what, I'm going to write it one more time just to kind of keep it cleanly and show you what I canceled. 5 is equal to, still had a pi in the numerator, so that's pi, 32 pi over 3 dr dt. And so now you'll be able to see a little easier that dr dt is 15 over 32 pi meters per minute. Okay, next one, another cone. Water flowing at a rate of 50 meters per minute from a shallow concrete reservoir, face or vertex down. So we got a cone that looks like this, which I'll stick down here. Base, radius, and height. So we again have height and we have radius. how fast is the water flowing when the water is 5 feet deep. So how fast is the water level falling? We want to know what dV, or no, dH dt is. And water is flowing out, so we're going to say dV dt equals negative 50, since this is a direction and water is actually flowing outwards. We also have a proportion to set up for the R and the H. We have H over R is equal to 6 over 45, which is the same thing as 2 over 15. So if it wants to know how fast the water level is falling, we're going to go volume is equal to 1/3 pi R squared H, which is equal to 1/3 pi. I wanted to solve for R, so we'd say 2R is equal to 15H, and R is equal to 15H over 2. So I'm going to take that and plug that in. We have 15H over 2 quantity squared times another H, and that's going to be equal to 225H cubed, or 225 pi H cubed over 12. So dV dt is 225 pi H squared over 3 and 12 cancel to get 4 dH dt. If I solve, I'm going to get 50 is equal to 225 pi times 25 over 4 dH dt. Then we can cancel some stuff. I can cancel 25 with the 50 to get 2, and I think that's it. Oh, this was negative 50, so anyway, we get dH dt equals, let's see, be negative 8 over 225 pi meters per minute. Next one, how fast is the radius of the surface changing then? This is kind of like before. We're going to take volume is equal to 1/3 pi R squared H. And instead of H, I'm going to substitute. So let's go back up to here and solve that thing for H. That would be H is equal to 2R over 15. So 1/3 pi R squared 2R over 15, and that's equal to 2 pi R cubed over 45. Deride that. dV dt equals 3 and the 45 are going to cancel, so it's going to be 2 pi R squared over 15 dr dt. Substitute, we know that negative 50 is equal to 2 pi. We don't know what R is, so I'm going to go plop over to here and say that R is 15H over 2. So if I bring that down here, R would be 15 times, let's see, 5 feet deep, so 15 times 5 over 2, which is equal to 75 over 2. So I'm going to plop that here, 75 over 2 squared over 15 dr dt. Keep that going. Dr dt equals, I'm going to actually start making this dr dt equals, so let's go, that'd be negative 50 times 15 over 2 pi, and then we have 75 squared is 5625 over 4. Let's see, the 2 and the 4 cancel. The 5625 and the 50 are going to cancel, and I'll just kind of skip ahead. You're going to end up with negative 4 over 3 pi meters per minute. For the next one, we have a particle moving along a parabola in the first quadrant, such that its x increases. So no matter how I kind of draw this, if I just kind of draw a parabola where part's in the first quadrant, it doesn't have to completely be there. It really doesn't matter. But it's such a way that its x-coordinate increases at a rate of 10 meters per second. So I can say dx dt equals 10 meters per second. And if I put a point here and kind of sketch this out and call this theta, it wants to know how fast is theta increasing, or how fast is it changing. What's the d theta dt? Well, I know, the only things I know about this like triangle here is that if this is x squared, because it's the formula of the thing. So I can actually set up the equation of the tangent of theta is equal to x squared over x, which is equal to x. And if I take a first derivative of that, I get secant squared theta d theta dt is equal to dx dt. And I want to know what d theta dt is. So if I solve for d theta dt, I'm going to get cosine squared theta times dx dt. Oh, sorry, that should be dt. Okay, so let's do this. If tangent of theta equals, and let's see, it says when x is equal to 3. So let's burst back up. When x equals 3, x squared equals 9. And tangent of theta is equal to y over x, which is equal to x squared over x, which is equal to x, and that's equal to 3. If tangent of theta is equal to 3, then y over x is equal to 3 over 1. And we kind of burst that and say y equals 3, x equals 1, radius equals square root of 1 squared plus 3 squared, so that's 10. I'm doing this to figure out that the cosine of theta is equal to x over r, which would be 1 over root 10. And plugging that back in here, the cosine squared of theta is 1 over root 10 squared times, and it says dx dt is 10, so that's 1/10 times 10, which is equal to 1. And our units are going to be in radians per second. Last one. 6-foot man walks at a rate of 5 feet per second towards a street light that is 16 feet above ground. So what I'm going to kind of do is sort of cast this thing here. We have a 6-foot man. It's a terrible man. Here's a street light. Street light is shining its light down like that way. It's causing a shadow on this man here. And the 6-foot man is walking at a rate of 5 feet per second towards the street light that is 16 feet above ground. That won't change. And here's 5 feet per second. And here's 6 feet for the man. At what rate is the tip of his shadow moving? Well, I know this is x, or I'm going to call that x. And we want to know at what rate is this whole thing changing, because the shadow is going to be following him. So I'm going to call that y. And for the purposes of this figure, I'm going to call this y minus x. And I'm going to set up like similar triangles here. We're going to go, let's take this triangle right here. 6 over y minus x equals, and I'm going to do the whole big one, equals 16 over y. And let's do some cross multiplying and manipulate this around. So 6y is equal to 16y minus 16x. Let's cut that into half. 3y is equal to 8y minus 8x. Move things around, and I have 8x is equal to 5y, or y is equal to 8x over 5. And if I start deriving both sides, I get dy dt is equal to 8/5 dx dt. We want to know what dy dt is, and we know what dx dt is. So I can actually kind of say this and say, okay, so that's 8/5 times, it says that he's moving at a rate of 5 feet per second, and that is dx dt. So dy dt is 8 feet per second. Notice how that was independent of anything else. His shadow is actually moving just a slight bit faster than he is. But I didn't have to know how far away he was. Okay. So if we kind of take this idea down to the next one, it says at what rate is the length of his shadow changing? This is a slightly different case with a slightly different picture. Still going to have this with the 16 and the 6. But this is still an x, but this is now a z here, because I want to know at what rate is z changing. In fact, I want to know dz dt. And it says at the point which he's 10 feet from the base of the light. So we know that x is equal to 10 here. And that's going to be useful. I can set up a different kind of proportion for this one. So now I can say that 6 over z is equal to 16 over, I could call that z plus 10. I could call that z plus x. I could call that y. Let's actually make that the y and see what happens here. So let's cross multiply. 6y is equal to 16z. Take the derivative. 6 dy dt is equal to 16 dz dt. I'm looking for dz dt, and I know what dy dt is from up here. So 6 times 8 is equal to 16 dz dt, or 48 over 16, which is equal to 3, and that would be 3 feet per second. So that really wasn't dependent on the 10 meters at all either. Interesting. We're done.